So, hello everyone, students and friends. I am Dr. Arvind Patil, Assistant Professor in Chemistry, working at SNJB's Arts Commerce Science College, Chandwad, affiliated to Savitribai Phule, Pune University, Pune. So, today we are going to learn something about chemical kinetics. It is the chapter allotted for SYBSc and course CHE-201 Theory Major 1. So, let us start. So, chemical kinetics is concerned with the rate and mechanism of chemical change. Now, roughly if we just see the reactions that are classified as homogeneous reaction and heterogeneous reaction. A reaction which occurs entirely in one phase is called homogeneous reaction, and a reaction which occurs two or more phases, that is called heterogeneous reaction. Homogeneous reactions are divided in gas phase reaction and liquid phase, that is solution. Here we are studying the kinetics of homogeneous reactions only. When we go to study the kinetics of homogeneous reaction, first of all we have to just learn about the rate of chemical reaction. So, what is the rate of chemical reaction? The rate of chemical reaction is the speed or the velocity of the reaction. It is defined as the change in concentration of reactants or products. In a chemical reaction, concentration of reactant decreases while that of products increases with time. Let us consider a general reaction to understand this rate of reaction. A gives B, means here A is reactant and B is product. Reactant may be more than one or product may also be more than one, but for example we are taking as A gives B, reactant gives product. So, as this reaction proceeds, the concentration of the reactant A decreases while that of the product B increases. So, the rate of reaction is equal to the rate of disappearance of A, and that is equal to, we can write that minus delta A molar concentration of A by delta T. So, you can just say dA by dt. So, this square bracket of A that indicates the molar concentration of substance A, and this minus sign that indicates the decrease in concentration of this reactant, not algebraically, that is minus. Okay. And we can define this rate of reaction in terms of product as the rate of reaction is equal to the rate of appearance of product B. Mathematically we can write B equals to this dB upon dt, means dB means change in molar concentration of B divided by dt means change in time. So, here the square brackets of A and B both considered as molar concentrations of this substance A and B. Now, this more to add about the rate of reaction. The rate of reaction is defined as the decrease in concentration of reactant in unit time or increase in concentration of a product in unit time. The unit of the rate are expressed in moles per liter per second for reaction in solution and moles per cubic centimeter per second for the reactions in gaseous phase. So, let us see the further concept of this chemical kinetics, that is law of mass action and rate law. So, the statement of law of mass action, the rate of a chemical reaction at any instant is proportional to the molar concentration of the reacting substance at that instant. So, this is the statement. The dependence of rate of reaction on reactant concentration at a given temperature is given or explained by this rate law of mass action. To understand this, we have to consider a simple reaction, that is general reaction. A gives product. Now, if square bracket of A mentioned here, that is the molar concentration of A, is the concentration of reactant at time t, then according to law of mass action, we can write as per this mentioned equation, rate of the reaction at time t directly proportional to the concentration of A, gives that we will give that equation 1. Then we can add rate equals to minus dA upon dt, that is directly proportional to A, that is concentration of A. So equation which shows how the reaction rate is related to the concentration is called rate law or rate equation. And this equation 2 is in differential form of the rate equation. If 2 or more reactants are involved in the reaction, the rate equation takes a complicated form. For example, let us consider the following reaction mentioned here, the A plus B that gives product. See, first of all, we have just seen about A gives product. Now we added one more reactant, A plus B, that gives product, or second reaction or second equation, that is A plus 2B, that gives product. So the rate equation for above reactions or these mentioned reactions are the rate equals to minus change in concentration of A with respect to change in time, directly proportional to molar concentration of A multiplied by molar concentration of B for first equation, first reaction, and for second reaction for A plus 2B gives product, we can write the rate law equation as rate equals to minus change in concentration of A with respect to change in time t, that is dt, directly proportional to molar concentration of A multiplied by molar concentration of B square, because 2 moles of B are taken in that equation. So we are, for better understanding, we are giving the numbers for these equations as 3 and 4. Let us consider a general reaction. Again, we can add something more about this, that is A moles of A plus B moles of B, that gives product. So the rate R at time t is experimentally found to be related to the concentration of species present at that time by an equation, that is R means rate equals to K square bracket of A raised to A small a into square bracket of B raised to small b, where the exponents small a and small b are usually integers or half integers. For example, half, 3 by 2, 5 by 2, 7 by 5, whatever that integers, half integers we can just take. Now it is taken that the power to which a concentration should appear in this predicted rate law is the same as the number of molecules of that substance involved in the chemical equation. The following experimental results show that the law of mass action does not always hold. See, the examples mentioned here, some 4 to 5 examples are mentioned. You can just see, that is 2HI gives H2 plus I2. That rate equation for this reaction is R equals to K HI raised to 2. Here the rate law, that is the law of mass action follows. Good. Now second equation, you can just say, second example, NaOH plus CH3Br, that gives CH3OH plus NaBr. For this, rate equals to K square bracket of NaOH multiplied by square bracket of CH3Br. So here also that follows. Now third, CH3CHO acetaldehyde, that gives CH4 plus CO, that gives R equals to K CH3CHO raised to 3 by 2. See, here the power is 3 by 2 for that molar concentration of CH3CHO in rate law equation. So here it doesn't follow that as per the molecules taking part in chemical reaction. So the further examples also shows the same, that is N2O5 gives that is 2N2O5 gives 2N2O4 plus O2. For this, as per this law of mass action, that should be R equals to K in bracket N2O5 raised to 2, but here it is not, 2 is not mentioned as a exponent because the experimental conditions are like that. It is only 1, means K under square bracket N2O5. Okay. So the next example, that is 2 KClO, that gives KClO3. So here the rate equals to K in bracket KClO. So here two molecules are taking part in this reaction, but exponent we have not put that 2, it is only 1. So with these examples you can easily understand that always that the number of molecules taking part in chemical reaction, that may not be the exponents of that particular reactants in that rate law equation to just study the law of mass action. Now the rate law for reactions 1 and 2 are predicted from law of mass action, whereas for reaction 3, 4 and 5 are not as predicted. So this means that the exponents in the rate law can differ the coefficients in the balanced chemical equation. Now the rate law must be determined from measurements of reaction rates and cannot be deducted from the reaction stoichiometry. Now let us see about the rate constant for that equation or reaction which we study kinetically. The proportionality constant K, that is the rate constant in rate equation, is called the specific velocity constant or rate constant or specific reaction rate. So the rate constant is characteristic property of the reaction and is different for different reactions. It depends on the temperature and it is usually increases with the rise in temperature. To define the rate constant, we will consider the reaction or equation that we studied earlier, that is minus dA upon dt proportional to A, that is minus change in concentration of A with respect to change in time directly proportional to molar concentration of A. So the equation can be written as minus d square bracket of A upon dt, that equals to K into square bracket of A. We put equation 1 here. Now here K is used, K in this equation is the rate constant when the concentration, that is molar concentration of A of the reactant is unity. The rate of reaction is equal to the rate of rate constant. So in this equation, according to this equation 1, you can just see that if suppose molar concentration of A is unity, so K multiplied by unity K, so rate will be equal to rate constant in that case. So thus the rate constant is numerically equal to the rate of the reaction when all the reactants are at unit concentration. So I hope you understood this. Let us see the further concept of order of reaction. So it is, this order of reaction is an experimentally determined quantity we have to keep in mind. It is obtained from the rate equation applicable to the reaction. See, order of reaction simply with theoretical equations we cannot predict. It is experimental quantity, and experimental quantity means we have to carry out experiments in the laboratories, and then only with the data obtained from that reactions we can determine the order of reaction by different methods. Now let us see how it can. Consider a reaction that involve several reactants A, B, C, etc. So let the rate equation applicable to the reaction be rate equals to K into square bracket of A raised to N1. Consider that N subscript 1, though what it is displayed in this slide, but consider as N1, N subscript 1. So, K in square bracket A raised to N1, small n1, multiplied by square bracket of B raised to small n2, multiplied by square bracket of C raised to n3, small n3. Means what? These are the molar concentration of A, B and C raised to n1, n2, n3 respectively. So, the rate of the reaction in equation 1, this indicates, is proportional to n1th power of the concentration of reactant A, that is molar concentration of A, and it is proportional to the n2th power of and n3th power of the reactants B and C, that is molar concentration of B and molar concentration of C respectively. So, the reaction is said to be of order N1 with respect to the reactant A. Similarly, it is of the order N2 and N3 with respect to reactant B and C respectively. And when we go for determination of the overall order of the reaction N, that N will be equal to N1 plus N2 plus N3, means the sum of exponents of molar concentration of reacting species in rate law equation that gives the overall order of reaction. Now, let us have the definition for overall order of reaction. The order of the reaction with respect to a particular reactant is equal to the power to which the concentration of that reactant is raised in the experimentally determined rate equation. This is individual order, or order is defined as the sum of the powers of the concentrations, molar concentrations of various reactants involved in the rate equation. It is called overall order of reaction. Experimentally determined rate law for the reaction, for example 2NO plus O2 gives 2NO2, which takes place in the gas phase at the room temperature and atmospheric pressure, is, we can just say, the rate, that is minus d in bracket O2 divided by dt, that equals to K in bracket NO raised to 2 and square bracket of O2. So, this is the rate law equation for this reaction represented here. The reaction is third order from the rate equation, rate law equation. Third order how? Because NO raised to 2, that is 2, and O2 raised to nothing means 1, 2 plus 1, 3. So, the overall order is here 3, and individual order with respect to NO it is 2, and individual order with respect to O2 it is again 1, but overall order it is 3, that is the sum 2 plus 1 equals to 3. Next example, 3 KClO gives KClO3 plus 2 KCl. The rate law equation for this reaction is represented here. The change in concentration, that is KClO3 in bracket, that is divided by dt, equals to K into in bracket KClO raised to 3. So, the reaction here also it is third order from the rate law equation. Okay. So, I hope you are understanding that how we can predict the order of reaction by mentioning or writing the rate law equation only. Without that we cannot predict the order of reaction. Let us see the another term used in chemical kinetics, that is molecularity of a reaction. Molecularity of a reaction is a theoretical concept, while order of reaction is experimental concept we studied. So, it is a theoretical concept. Molecularity of reaction is a theoretical concept and is based on the mechanism of the reaction. Each step in the mechanism of the reaction is called an elementary reaction. The number reactant, number of reactant molecules that are involved in elementary step represents the molecularity of an elementary reaction. So, the reaction where the example we can just take CH3CHO gives CH4 plus CO. In this equation, in this reaction, only CH3CHO, one molecule is taking part in reaction. So, molecularity for this reaction is 1. 2HI gives H2 plus I2. Here 2HI, two molecules of HI are decomposed to give H2 plus I2. So, the molecularity is equal to 2. Third example, NaOH plus CH3Br, it gives CH3OH plus NaBr. Here the two molecules, means one molecule of NaOH and one molecule of CH3Br are taking part in this reaction, hence the molecularity is 2. So, likewise in 3KClO gives KClO3 plus 2KCl, the molecularity of this reaction is 3. On the basis of molecularity, the elementary reactions are classified as unimolecular, means involving one molecule only, bimolecular, which involves two molecules, or termolecular, involving three molecules. So, the order of the reaction may be 0 or even fractional, but the molecularity of the reaction can never be 0 and fractional. So, this is the major difference in order of reaction and molecularity of the reaction. So, we can just keep in this mind. Now, if we go for watching or studying the difference between the order and molecularity of a reaction, so you can revise some points which we studied when we have seen order of reaction and molecularity of reaction just now. So, if we compare in order of reaction, it is the sum of powers of concentrations, molar concentrations of reactants involved in the rate equation, while the molecularity of reaction, you can write it is the number of reactant molecules involved in the elementary step reaction. Second point, we can put in order of reaction as it is an experimentally determined quantity or property, while in molecularity of reaction we can express it is an theoretical property, not an experimental property. In order of reaction we can write it can be fractional and can be 0, but in molecularity of reaction we put that it cannot be fractional or cannot be 0. And next point we can add it can be changed with experimental conditions like concentration, pressure, temperature, etc. for order of reaction. But in molecularity of reaction it is fixed for a reaction, it is independent of experimental conditions of the reaction. So, these are some differentiating points between order and molecularity of a chemical reaction. Now, let us move towards the integrated rate law expressions. Integrated rate law expressions that gives the concentration of reactants at any time t during the course of reaction. Now, mathematical expression for different order reactions we have to see. Initially, we will start from 0 order reaction. Now, just now we learned about the order of reaction. Now, we are just taking the 0 order reaction. Means you might remember that 0 order reaction means what? In rate law equation of such reaction, the exponent of molar concentration will be 0. So, these 0 order reactions are uncommon, but some heterogeneous reactions has order of 0. The rate of 0 order reaction remains constant and it does not change with the time, as it is independent of the concentration of the reactant. So, rate equals to constant, that equals to K0 for 0 order reaction. K0 is the rate constant for 0 order reaction. And let us consider if Ca, C subscript A is the concentration of a reactant A in a 0 order reaction at time t, we can write equation 1 as rate equals to that rate change in concentration of reactant, that is dCA divided by change in time dt, that equals to k0. Give this equation number 2. Now next we can just, if here in this, if a mole is the initial concentration of A, that is the concentration at the beginning of the reaction, and if X, that mole react in time t, will be A minus X mole. This is Ca, substituting the value of Ca in equation 2. I hope you understood that here the small a, that is the mole, is the initial concentration of A, and small x is the mole reacted in time t, and the remaining concentration after time t will be A minus X mole. So here if we substitute the value of Ca in equation 2, we can get minus dCA upon dt, that is change in concentration of A with respect to change in time t, is equal to minus d upon dt, A minus X equals to minus dx upon dt, that equals to k0. Now this is the rate constant we have. Now this put as equation number 3. Now this equation 3 can be integrated between the limits t equals to 0 to t is equal to t for time, and x is equal to 0 to x is equal to x for x, that is the decrease in concentration or change in concentration. Rearranging this equation, we can write dx is equal to k0 dt. Integrating equation this 4 between the above limits, we get that integration of x0 to x dx is equal to integration of t0 to t, that is k0 dt, and that equals to k0, because being constant it can't be integrated, so it can be put by the side of that integration, and k0 integration of t equals to 0 to t dt. Now this k0 here, it is the constant at a constant temperature, is taken out of the integral sign. Now this, solving this integration, we will obtain the equation x is equal to k0 t. Now this put as equation 6. Now this equation 6 is the integrated form of the rate constant for a zero order reaction. Now this equation can be used to calculate k0, that is the rate constant for this zero order reaction. Now the same way we can just this integration of this equation 4 is given here to obtain the final equation, and then the further concepts, as up to still now we have studied up to zero order reaction. The further in next class we will go for the reaction kinetics of first order reaction, second order reaction and third order reaction, and their characteristic properties. Okay. So here we will stop, and thank you very much.